Great, thank you, Raphael. Can you guys see our screen okay and hear us okay?
Yes.
Okay, great. We'll kick it off here with some quick introductions. Good morning, hello, everybody, wherever you are in the world. I'm Doug Norton. I'm the Chief Marketing Officer here of InspireSemi. We'll give you kind of a quick overview, and then we'll get into some of the tech. With me today is our co-founder and CTO and president, Alex Gray, and also our Chief Operating Officer, Thomas Fedorko. And then last but not least, Teo Hall, one of our principal software engineers here. So our backgrounds are here. They're also on our website if you want to look at us. But the main thing to tell you about this team is we're very experienced. We've all got both public and private company startup experience. We know how to scale orgs, but we also know how to roll up our sleeves and get things done. So that's what we've been doing with a pretty small core team here. We've got a lot accomplished, and that's one of the ways we get it done. We are actually a public company on the Toronto Venture Exchange. We did that back in late 22. So I have to show you this disclaimer that I'm sure you've seen before, which basically says, don't take anything we're saying here as anything to buy our stock or not. So to kind of position this, really the way you think, I thought about this when I had to bubble it up to like 30,000 feet. What we're doing here was in the good old days before we had floating point units in the PCs. We plugged in a math coprocessor chip and everything just worked. Everything went faster and all that. It was good stuff. For the last 25 or 30 years, we've been trying to find something else in the high performance world to do a similar kind of thing. And I think we all know that NVIDIA has been the most successful at this as they pivoted from their gaming origins with their GPU to go kind of general purpose GPU. But even that has had some applicability in HPC. Very good success in AI, but for HPC, engineering, scientific apps, only some applications benefit. And I think the biggest problem too is that it's a lock-in solution. You write to CUDA and you're kind of stuck with NVIDIA. Doesn't work on an AMD or an Intel GPU or a 10 torrent GPU. And likewise, you write to AMD and it doesn't work on the others, etc. So nobody likes that. It's kind of painful. So we're out to solve that. We've built a custom-built RISC-V based solution here that will likewise plug into existing servers via PCIe slot. But we've made it versatile with the open software ecosystem of RISC-V and make it easy. We're not trying to adapt, or I would argue force fit, shader engines or other type tech to solve these problems. So, a lot of people think, if you listen to the marketing hype that GPUs do everything. We all know better. They have some applicability for HPC. In financial, sure, Wall Street, they use GPUs, but for Monte Carlo simulations and things like that. But they can't use them for trading because they're not deterministic. We'll talk about that in a bit. And they don't do graph analytics, which is what's being used nowadays for all the fraud detection and anti-money laundering. Likewise, yes, they're used by oil and gas companies to find the oil with seismic. But once you've found it, the other half of the problem is most profitably and optimally producing them, which is reservoir modeling and simulation. Again, these are all CPU workloads that don't lend themselves well to GPUs. We see this in many other areas. CFD, all the leading CFD codes really don't work on GPUs. Life sciences with genomics, things like that, again, CPU workloads. Climate weather modeling, CPU workloads. So what we have built is basically a highly differentiated supercomputer cluster on a chip. We've packed over 1,500 64-bit RISC-V cores on a chip, and we can get 4 of these onto a 3/4 length PCIe card, delivering over 6,000 highly interconnected CPU cores. So this gives you very large scale computing power. It scales up to 256 chips. And we focus not only on performance, but also on cost and energy efficiency. So those are some other key metrics we look at internally: performance per dollar, performance per watt. So that's kind of the high level. For this audience, we tell a lot of people why we chose RISC-V. We have a whole backup set of slides that I presented, like the IEEE and stuff. But we looked, early on at various tech, including ARM, and we chose RISC-V for several reasons. It's modern, it's efficient, and it's open. It's an open standard. And that was really important because even ARM's been around. It's got about 20 years of baggage in it, and x86 still has to boot DOS, so that's just not a good thing when you're doing something like this. So having a modern superscalar architecture that supports out of order and vector and the ability to extend the instruction set were very big deals for us. So again, 1,500 cores per chip. It's comparable to pretty close to GPU shader count, but these are independent CPUs, all 64-bit. And they're highly interconnected. We'll get into that with our mesh network fabric for very high bandwidth, low latency, which is, again, really important to make this work and make it deliver for real world applications. We talked about energy efficiency and supporting RISC-V, of course. The whole goal there was to leverage this existing ecosystem, not make people change all their code. So that's what we've done. And then we've got some really great go-to-market partners here, as you can see, including, I saw Fabrizio on here from E4 in Italy, which is great as well. So this covers high volume capability across multiple markets and geographies, and gets us going here. This is some customer sample feedback we get from customers and partners. We actually just issued a press release back in February or December with those top 3 quotes very public in the press release. And there's a lot of people saying this is really what people want. That quote I had at the top of the markets we addressed that says, what people really wanted, not yet another GPU. That actually came from the Chief Research Officer of Intersect 360. He said, my gosh, this is what people have wanted for 10 or 20 years, and you guys are doing it, delivering this type of capability. So, yeah, again, some of that's on our website as well. With that, I'll hand it off to Alex to tell you a little more about exactly in the hardware tech.
Sure thing. Thanks a lot, Tyke. So the first headline number people like to look at is just your raw performance, teraflops, things like that. And we'll give you those numbers in a bit. And of course, I want to compare it to, GPUs, which are actually pretty good when it comes to raw horsepower. So our objective has always been to match them, at least for an equivalent process node, on raw teraflops for double precision and ideally single precision floating point, which is what our target market needs more than the low precision AI stuff. So we match their top line numbers, and of course we expect much greater utilization because this is a CPU architecture with extremely dense interconnect between the CPUs. GPUs lose most of their peak performance due to the inability to communicate between cores, high latency, even when you can communicate between cores, and the SIMD nature there, where 128 shaders have to do exactly the same thing on exactly parallel data streams, which just isn't the reality of many applications. Energy efficiency is another huge deal. Some people we've known for a while might remember we started out in the blockchain world, where energy efficiency is life and death. Even if you don't have the fastest processor, when times are tough, which they often are in that world, it's the people who have the best energy efficiency who survive, and everyone else can't keep their lights on, literally. So we've brought some of that heritage into this new general purpose compute platform, and I think it's paying great dividends. We have a great position in a world where even mainstream data centers can barely deliver enough power to the racks to use the equipment they have. And they care a bit about their multi-million-dollar power bills. Our price point is also pretty competitive, or it can be. We're using a bit older process node, 12 nanometer, and we have a very, very dense chip. Our core is very small, and so we can get a lot of performance for a fairly low cost from the foundry. Doug's talked about the huge range of markets we can serve, being a general purpose CPU. We mostly talk about HPC, but literally everything that CPUs do today is a potential market for us. Even mainstream servers, some of those applications can use as many cores as we have, and each of these cores is a first-class core. It can do everything your x86 can do, or at least everything an ARM can do. Porting is straightforward. I think we're preaching to the choir on that. It's just a recompile to go from x86 to RISC-V. Of course, there's always lots of optimization you can do for a given machine, but that's true even when you're going from one generation of Xeon to the next. And double precision has been a big differentiator for us. GPUs obviously can do it, but they don't really excel at it. And most of the other accelerators that have been coming on the market recently have been AI focused and not focused on double precision performance, which we find many HPC customers need. And lastly, determinism. We've discovered more recently that that's a really big deal to a lot of customers, especially in finance and other mission critical applications where you can't have a 10 millisecond delay while the GPU scheduler figures out what it wants to do. And you can't have the variance in results that comes from your order of operations changing, rounding errors being applied at different times, and then getting multiplied and actually changing the outcome of the calculation. And say a little more about these benefits. Doug, is this our only slide on latency?
Yeah,
okay.
The main one. We do go to determinism in more detail.
Good. So on the right picture there, some of you are probably familiar with GPUs, where even on an L2 cache hit, you can have 100 or even 200 cycle delay as you go to that big central cache or some other shared memory. And that's about the only way to even communicate between CPUs. There's not a lot of direct interconnect between them. There is some more local shared memory, some people surely know. But moving large amounts of data between cores really means pushing it out to memory and reading it back. And if you're lucky, that's an L2 cache hit and a few hundred cycle penalty. Our mesh network, which we'll talk in detail about later, gets that down to about 1 to 20 clock cycles. 1 clock cycle to talk to a neighboring core, and 20 to talk all the way across the chip with random traffic patterns. Anything else we should cover here?
Yeah, I think the key is it's both deterministic. It gives you good deterministic, and for a lot of applications, predictable performance is just crucial. We're hearing this in various markets, including everything from Wall Street trading floors to using smart weapons or gamma knife surgery, things like that.
Right, a little more on the determinism. I think we gave the overview. The important things are that we don't have a scheduler that's inserting more or less random delays between steps and changing the order of steps. In some cases, you're doing very high-level kernel calls through some framework, especially the AI applications, and you just don't control when it's going to send those to the GPU and what else the GPU is working on. There's a lot of also secret hardware inside the GPUs that decides when individual threads get run. I know there's been interest recently in more barrel-like processors where you at least know when your thread's going to come up, but in a GPU you don't even have that. Plus all the hardware overhead of having to have 1,000 threads on hand to run at any given opportunity. That's why you have such huge register spaces in GPUs and don't necessarily get the benefit you might hope for from having that much register space. It's just too many threads that have to be in flight at once because of latency. And as I mentioned, changing the order of operations can change the results. Even a tiny floating point rounding error can get multiplied by a big number and then become significant in the output. Anything else we should say here? There's obviously a range of, depending on how critical determinism is to your application. If you do bare metal programming, which is much more feasible on RISC-V than on a secret GPU ISA, you can get down to nanosecond level determinism. We also allow direct management of the local core memory. What would normally be an L1 cache, you can make into a directly controlled scratchpad. And so then the programmer controls exactly what's in their local memory and doesn't have to guess at which cache they're going to hit or not hit for a given operation. So you actually can get real-time nanosecond level precision if you need it, or even if you don't go to that much effort, you still have much higher determinism than in a GPU or some other accelerators.
Yep. So this lets us go after a lot of applications that otherwise would probably require an FPGA, and oftentimes it's just not worth going to the pain of coding the Verilog and doing all that to do it. So.
High-level specs, we're looking about 6 to 8 teraflops per chip. This is our 12 nanometer half-particle Thunderbird Gen 1 with 1,500 cores. We can put 4 of these chips on a card. That's a standard 3/4 length PCIe accelerator card, same as most data center GPUs. So that gets you the same teraflops per card, or comparable to an H100, at least before you bring the tensor cores into the picture. Energy efficiency is very good. It's actually likely better than this 50 gigaflops per watt of double precision. Latency, as you mentioned, is around a 20th of what you get in some other platforms, and the power consumption obviously depends very much on the application, but about 30 to 60% lower than you would typically see in other platforms. I know that we actually have some folks on the call who've done very impressive things in power as well for certain applications, but comparing ourselves here to GPUs and other mainstream platforms at the moment. Let's move on. Overview of our architecture. Our core is a 64-bit superscalar RISC-V, of course, CPU core. We have both first of all, this is our own design. We didn't license this from anyone. We've been working on it for a while and really squeezing performance and moreover area out of it, area and power. We've minimized, I think, about as well as it can be. We have 2 versions of this core. One is a 4-issue and one is an 8-issue. They do implement the whole RV64 GC or IMA FTC instruction sets, including privilege, so we can run Linux and other operating systems on this core without any special software trickery. We have a pretty good reorder buffer. We can reorder instructions pretty well. It's not as deep a buffer as you would find in modern application like ARM processors. It's only about 16 to 32 slots deep, but for reasonably optimized HPC code, that's all you need. Ideally, you would need no reordering, but of course, no one wants to spend months thinking about exact which instruction goes on which line. So that helps. Floating point, including some mixed precision. We mentioned single and double precision. We also are working on BF16 support and mixed precision operations. A lot of the AI features that would leverage that BF16 are probably getting pushed to our Gen 2. There will be supporting some basic tensor and matrix operations just to make better use of the data path. Vector is another thing that we had planned for this. We actually have all the hardware to do the vector calculations, but adding all the decodes has been more than fit in our schedule. And there's enough uncertainty out there in that that standard and the compiler ecosystem at the moment that we're going to let that go to Gen 2. But with our superscalar architecture, we actually can get similar throughput to vector operations, effectively a 256-bit wide data path, doing 4 full double precision operations per cycle in a very small core. And since we're targeting HPC applications that typically have a very tight loops, those all fit comfortably in instruction cache. So the instruction bandwidth savings of vector aren't as critical to us yet. Nevertheless, we do look forward to adding that support next year. What else should be mentioned about the core? Memory, we have about 64 kilobytes of SRAM in each core. Can use it like an L1 or as a scratch pad that the programmer controls. Obviously, coherence is a big deal on a chip this size, and that's also something that we're supporting as well as we can at this point, but we'll have a fully coherent platform, I think, on our next generation, including CXL at the interfaces. So many of these can be integrated in a fully coherent system. Our fabric, we've already bragged a bit about the performance, but we really started this design with the physical layout in mind. A lot of people just write RTL, and that's great, but when you get to things like interconnect, where you really have to worry about routing resources, the number of wires, which are actually the scarcest resource in these processes, it's really good to be looking at the physical design right from the start, which we've been doing. So we use essentially every wire on the mid-range routing layers of the manufacturing process. Every track is utilized for this interconnect fabric, which is a Manhattan grid that crosses over every core and connects by abutment to the neighboring cores. That gives us 32 64-bit data lanes in each direction. Those lanes run at the same clock as the core, so you're transferring 64 bits of data every clock cycle, about 1 gigahertz, across each of those lanes. Excuse me, we have 16 lanes going each way on each edge of the core. So 128 total lanes of bandwidth. That's hundreds of terabytes per second local and tens of terabytes per second global, even with pretty random traffic. A lot of the applications we've looked at from the beginning do have truly random traffic, things like graph analytics. You're tracing edges and you have no idea where that edge is going to lead. So you can't really order things physically. So that's a big advantage. Obviously, anyone can get high bandwidth just pushing things through a systolic array, but we're able to route things in real time across this big chip without high latency, even when the traffic patterns are random. And this uniform cellular layout lets us scale this thing indefinitely. We've actually already done some porting to 4 nanometer, and it's very easy just to tile 10,000 more of these cores onto a single chip. Finally, the right column is our top-level architecture. This is our Gen 1 12 nanometer design. It has 1,536 CPU cores. It's a 24 by 64 array. Those cores can be used in either a SMP, a symmetric model, or in the HPC cluster style, where in the SMP model, of course, they're all in one. They all see the same address space, and they're managed by the single operating system. Whereas the HPC cluster model, you could run multiple operating systems on a single chip, or multiple operating systems across multiple chips, and use a message passing layer like OpenMPI, which incidentally we have recently gotten running in a emulation environment. So that and much other software ecosystem is already ready. We'll get into that later. This network of ours that crosses over the cores is extensible across multiple chips. It can be bridged over PCIe, or also we're working on our native, running our native protocol over the same SerDes that PCIe uses, which gets rid of some of the overhead of PCIe. We have 128 lanes of that interface. 128 lanes, they all have PCIe controllers attached. So you can run up to 16 PCIe devices controlled from this chip. You see the 8 banks on the top and bottom. Each of those is bifurcatable. So you can have 16 endpoint devices attached to this chip, or this chip can be an endpoint attached to a host server. Also around this, scattered around this chip, we have some algorithm-specific accelerators, mostly cryptography oriented, and your basic interface stuff like UARTs, I2C, SD card, QSPI flash, all the basic interface jelly beans. And this layout has been fully routed, and it's DRC clean at the top level, which has been a huge accomplishment for our very compact team. We're really proud, and we're looking forward to getting it to the foundry imminently. This is the board level design. We mentioned putting 4 chips on each of these boards. That's a very dense board in a 3/4 form factor, but it does work. It's routable. And each of these chips has 6 DDR4 memory channels, which also support LPDDR4. The layout you see here, those are LPDDR4 x32 chips attached to each channel. That lets us put about 48 gigabytes, 24 gigabytes on each chip, and 96 gigabytes on the whole card. Excuse me. And I think a future layout will be able to support twice that amount, so up to 192 gigabytes on a card. And this is being LPDDR4, very cheap memory. Again, we hit an attractive price point, and we have a much simpler supply chain than if we'd done HBM. I think on our next generation, you will see HBM as well. That's obviously critical to some applications.
Yeah. Early feedback, just so everybody knows, as we reached out to prospective customers and national labs and all that, was if this was an AI focused chip, it would have to be HBM. But it was very, very consistent that everybody said, since you're going after HPC, we'd rather have more and cheaper memory. So hence the decision to stay DDR for this device. But as Alex said, next time, now the supply chains have gotten a lot better and HBM's gotten better, we'll likely be doing that on Thunderbird too. Teo?
Yeah. So our physical design and sort of what the design architecturally that we have been shooting for, our software ecosystem has been very open, leveraging open source projects and trying to avoid lock-in of any sort for any of our partners. So we don't have any proprietary software stacks or things that you have to rewrite your algorithm as you would when trying out a whole new architecture for GPU, per se. We're using open compilers. We're starting right now. We have the most testing on GCC, but we're really just working with partners and picking the right tools. We've interfaced with CodePlay and One API. We have an address accurate QEMU model. We have our chip will use GCC and GDB just natively. And we've ported a couple of operating systems to some of the cores, both allocating just a subset of cores and having the other cores be co-processors. And also we've toyed with the idea of just having all of the cores just natively run and scheduled by an OS. But those operating systems are just Linux Kitten, which has made the rounds for HPC, and then a couple of RTOSes, specifically for RTOS. But right now we've done the most work with GCC and are moving as we mature and work with our partners to support the most amount of tools and just avoid lock-in of any kind for our partners. Just stay very general purpose.
Great. Thomas?
Yeah, so I think this audience is probably quite familiar with TSMC, the world's largest and most advanced wafer fab in the world. We're very fortunate to have partnered with TSMC for all of our wafer foundry requirements. TSMC, of course, invests huge amounts of capital into R&D, and so they not only have our process node that we're using today, which is a 12 nanometer process node. We selected 12 nanometer because it delivers on the price, performance, and power targets that we had set for the Thunderbird project. It was also readily available, so we could secure the capacity that was required for our ramp, which is going to be quite aggressive this year. And so that capacity has been secured. Obviously, they also will be delivering our next gen process, which we'll talk about some at a high level. But we selected the 4 nanometer node for that process, and so we're quite confident that the 4 nanometer capacity will be available as the new foundries in Arizona come online to supplement the ones that are currently in Taiwan. ASC is our OSAT. They are also the world's largest and most technologically advanced OSAT in the world. We have partnered with them to do the package design for this project. The package is quite complex. It's a 50 by 50 flip chip BGA package with a 14-layer ABF substrate. And so IMEC and ASC have partnered together to work and develop that package substrate for us. IMEC is our value chain aggregator. We partnered with IMEC because they could open doors and get us early access to both the 12 and 4 nanometer process node in small quantities and allow us to get through prototype and early production ramp. And at that point, we'll be taking those relationships direct. but they've been a very nice partner for us and getting us early access to the technologies we needed for this project. We like to show this slide because it kind of illustrates how important die size is with defect density. As we mentioned, TSMC is not only the world's largest, but they're the highest quality foundry in the world. Their 12 nanometer process node typically runs at about 0.1 defect per centimeter squared. And so your die size has a direct relationship to your yield based on that defectivity. And so the smaller your die is, the much more advantageous it is from a cost perspective. And so a single particle on a very, very large die will take out that entire die and a tremendous amount of area, which is both costly and challenging from a yield improvement perspective. So our smaller, much smaller die for the same level of performance affords us a really nice margin cushion that we enjoy with this project. So as I mentioned, our current generation of Thunderbird is on the 12 nanometer process, but our next gen is going to be on the 4 nanometer, TSMC's 4 nanometer process. We've already taped out a test chip on their 5 nanometer process. 4 nanometer is optical shrink of the 5, so it's very representative of what we'll achieve. This team, there's only a handful of companies in the world that have a successful product on 5 nanometer from TSMC, and InspireSemi, we're very proud to say InspireSemi is one of them. I'm quite confident we are the smallest team that has ever taped out a product on 5 nanometer. That product came back, we custom built the substrate for it, and we have done a fair amount of validation, and it actually meets all of our performance and power targets that we set, and we set some very aggressive targets for that project. And so it did require a full custom layout and has been fairly optimized, but we're quite pleased. When what this does is gives us a tremendous amount of confidence that as we roll from our Thunderbird 1 project and 12 nanometer down to our next generation 4 nanometer, we are very confident that we'll be very successful in that endeavor. So the 12 nanometer schedule right now, as Alex mentioned earlier, we are very, very close to tape out. We expect that in the next handful of weeks. And we'll finish that. We expect chips back from fab around the middle of Q2. We'll spend 3 or 4 weeks in detailed validation, characterization, and we'll make our first customer shipments very early in Q3. And we expect to be ramping into production in late Q3.
Indeed. And we do plan a fast follow on Thunderbird 2. We've talked a little bit about it, so that work will happen, once this thing is done. And we'll be cranking on that. This is kind of a quick summary, if you will, across different technologies that people might do. Obviously, we've talked a lot about GPUs, and they have some applicability to HPC, but again, they're great at AI, and in some cases HPC. But we, with an all CPU architecture and based on RISC-V, open, all 64-bit double precision, we can go after pretty much all applications, as Alex said. But we're not just disrupting on that. We're disrupting at every level. We talked about energy consumption. The 150 watts a chip will be kind of max. It's probably typical, might be more like 50 watts a chip. With the initial card, we do have a 4-chip, which we'll come out with, but we also plan to offer a 2-chip version of this, at a low price of like $6,500. So you look at that, compared to GPUs and other options of like bolting together lots and lots of servers with InfiniBand network and all that. This becomes a very, very attractive option that's going to disrupt at every level. Things that can run, price point, energy efficiency, scalability, everything. We have an early access program running. We've announced some of the customers that are in that back in that December press release. But we've nicknamed it Thunder and Lightning and the Legend of the Thunderbird. Where the Thunder will be, the early emulator, and then the Lightning will be the actual full-blown PCIe card once that's available here a little later this year. So the whole objective of this is to jumpstart adoption, of course, in software applications to get going on that S curve that we all know exists, because after all, hardware is simply a platform for software, and we get that. So we want to make sure we pick the right partners early and allocate them the right hardware and really take good care of them and work closely with them. But we also wanted some really good smart customers that would give us the right feedback for Thunderbird 2 as we add more AI capabilities and things like that. So For that reason, we did cap this program at a limited number, and they had to identify a good application and especially allocate the technical resources. And frankly, that was the challenge we had more than anything, was people who just had the time to do this and the people to dedicate to working with us on this. So that's it. Teo talked about, we do have an address accurate QEMU model. We're shipping this FPGA emulator dev board with a fraction of the cores, of course, on it to early customers right now, and all relevant software for both the FPGA and then later the PCIe boards. They get that. So really strong interest. We've received a number of POs and commitments already for this, and we're off and running. We do have a couple openings left if the right people want to come in. It's not quite closed yet. So that's the main thing we had for you. Happy to take any questions and go from there.
Yeah, so we have some questions in the chat. Also, if anyone is willing to ask a question verbally, please raise your virtual hand so I can allow you to speak. I'm not sure if you can follow the chat for the questions, but there is I believe let's see, the first one here is about PCIe. Doesn't the PCIe link become the bottleneck by bringing back and forth the computed data?
There's great points. So in our basic PCI accelerator card, it is just an X16 Gen 4 link. That's this always been possible in this iteration. So that's going to be the same sort of bottleneck you'd see with other single card accelerators. I think one improvement we can make there is that, first of all, we have 4 of these chips on a card, and we have a lot more bandwidth on the card. We're not limited by the edge connector or anything else. So we can see like 10 times as much bandwidth or more between chips on a given card. And we're even exploring with one partner the possibility of doing a motherboard-sized array of these with 64 or more chips on them. So the chip-to-chip bandwidth is not at all constrained by connectors anywhere. And in that case, we can get, I think it's about 256 gigabytes per second per chip of aggregate bandwidth for the system, which is quite a bit more than you can bring across any PCIe edge connector. And of course, our next generation next year will be moving up to much faster SerDes, at least PCIe 6, and the raw SerDes interfaces can then go to 112 or even 256G. We might even have more lanes. So next gen is safe to say terabytes per second of bandwidth per chip, and we'll still have this many chip card architecture so that you can get even up to hundreds of terabytes per second in a single array of these devices. So we're definitely very conscious of that need for communication bandwidth.
Yeah, and CXL is planned for Thunderbird 2, and that's when the CXL spec gets much more interesting anyway, to version 2 and beyond.
Another question we have here is the program, I believe you have answered that before, but is the programming of the device similar to the GPUs?
In short, no, it's nothing like the GPU model. You take your x86 code or any other CPU code, that can be C or C++, even Fortran, or just RISC-V assembly. And as we get Linux and other things up, it even becomes possible to consider Python and other high-level languages. That's sorry, I lost track of the question.
He's also asking how do you specify what cores run what piece of software. Right. I answered it in chat, Alex.
Okay, good.
But basically, it's completely up to software.
Well, yes.
So the hardware is completely agnostic as to what runs on what, shall we say.
Right. So you can leave it as an operating system like you would in x86 or other applications platforms. Or if you want to get to a low level and program this thing bare metal assembly, then we have a simple library that lets you send threads to specific cores. If the programmer
and that same API will be used to like bring another core out of reset and bring it into the SMP cluster, for example, right? Or tell it to go run this other RTOS and then it's often on its own little island.
Right. There's another question about coherence. That's honestly one of the things we're scrambling to optimize late in the cycle here. It is quite challenging to keep 1500 cores coherent. There's a lot of applications that actually prefer to use the in-core memory as a scratch pad, and that may be what we focus on initially. Our network does support coherence protocols. You can send, I think people here are probably familiar with TileLink and other similar protocols. We have the multiple channels to support TileLink with the appropriate prioritization so they can't deadlock, et cetera. We just have not had a lot of free time with our tiny team to prove that out. So I think you may see full coherence in Gen 2. Obviously, there is overhead that comes with that. And with this initial platform, it'll be more optimal to allocate the scratch pad or local memories by hand.
Yeah, a couple of things. First of all, for those who don't know Mark Karasik, he is part of our team as well, one of our key principal software engineers. And I know he's presented on a couple of these sessions in the past.
Yeah, hello, everybody.
And the other thing I'll just add is we're finding a number of our early partners are telling us, looking at this and going, my gosh, you could not have built a more perfect architecture for graph analytics. And I was at the Dell HPC annual event like a year and a half ago, and Thomas Sterling came in. They brought him as a guest. And for those who don't know Thomas, he's the father of the Beowulf cluster. And Thomas had a really great prediction. He said, I'm going to kind of tick everybody off at the end of this. I'm just going to warn you right now on slide 2. My prediction, which is that the von Neumann architecture is dead. Everybody should be designing architectures for graph. And we saw when Jack Dungara was awarded SC22, he kind of got up and said the same thing, the inventor of the LinPack benchmark, that that was a long time ago when we were doing dense matrix operations, and the world is going to sparse matrices. Those are today's applications. So graph analytics is a super example of that. We met with the top ISVs in that space. They all agree they're chomping at the bit to get this. This architecture lends itself very well to that. And in fact, there's a potential good AI kind of bolt-on application that this might be a great application for as well, which is with these big LLMs, if you could run and kind of right on the heels of that, a big graph analytics against all known facts, you could really clean up some of these models and the predictions and stop the hallucinations. So we're going to be investigating applicability there with some of our graph partners as well.
Great. I believe you have answered all the questions they have asked. So, folks, is there any more questions you'd like to answer? Or, sorry, you'd like to ask now? You can paste or put that in the chat or ask verbally if you will.
Yeah, we certainly appreciate the interest and the opportunity to share more what we're doing here now that we're about to get this thing in production. And we look forward to helping disrupt this market and delivering what people in applications really want.
Sure. I'd like to thank you all for participating. Thank you for joining. Thanks for sharing with everyone in this technical session. The next technical session will be around RISC-V security. It's going to happen at the end of this month. So stay tuned for the invitation so you can all participate and join and participate. So everyone, thanks for joining InspireSemi, and thanks for joining, explaining, and showing your product. Thanks for all the great details. So this session was recorded. It's going to be available in our YouTube channel, maybe 1 week or so. And then I'm going to share with you all the slides as soon as I get them. So thank you everyone for joining. Thank you for your time, and see you in the next technical session.
Thank you all.
Thanks, everyone.